here we go. We'll see if the rest of the class trickles in a minute or two. So we talked about the final exam yesterday, right? We talked about the fact that it's going to be chapter 5, and then I will give you a list of other stuff that you need to be able to do. What I think we forgot to talk about was you can use all your previous cheat sheets, and then you can make a new one for chapter 5. 1/2 page, one side, same directions as usual. So you can use all the previous ones, plus you can make a new one. Any questions there? I still owe you a list of topics. My goal is by the end of the week. I think that's what I said yesterday. Anything for questions there? Okay, questions on homework, which is due on Friday from 5.1, 5.2, 5.3. Same thing as usual, due at 2 o'clock, and I only need one submitted per group. Anything for questions there?
I have a question on not the stuff that we just got, but the stuff before it with like problems 24 and 27.
Yes, hold please, I'm getting my book.
Okay.
Keep talking.
It's just a really quick question, but like after you do like the matrices, sorry.
Thank you.
And stuff, when can you like simplify? Because I think that for both 27 and 24, there's like, I don't know, they simplified, and so it's a I don't know, like the answer is different.
Okay, hold on please. So are we in 5.3 or 5.2? Or page number?
3.
345, 346?
364.
Oh, okay, sorry, I'm looking at the wrong section. Okay, maybe this will make more sense if I look at the right section. Here we go. Okay, 24 and 27. Okay, so verify that the given vectors are solutions. That part's fine, right?
Yeah.
Okay.
If I get like for the first one, for like x, like the vector x1 prime or whatever, I have like 3e to the 3t and then negative 3e to the 3t.
Yep, that's right.
So, but then like when you put it in, do you use 3e to the 3t and then negative 3e to the 3t as well?
Yes.
Like in the bottom, you do the Wronskian?
Yes. So we're doing two different things. When you're doing the Wronskian, you want to just put the vectors in. So whiteboard here. When you do the Wronskian, you want, so the determinant of vector x1, I'm going to draw a line for a column marker, vector x2 in this case. That would be your Wronskian. So you don't use derivatives at all in this type of Wronskian. You do in the previous ones that we did back in chapter 2. In this one, you don't. You just have all of these vectors, so there's no derivatives in the Wronskian. Am I answering anything close to what your question was?
Okay, so like for the Wronskian, you do e to the 3t and negative e to the 3t?
Right. So the book pulls it out, right? So it's determinant of e to the 3t, negative e to the 3t. And then the second column, this is 24, would be, right, e to the 2t and negative 2e to the 2t. So you want the determinant of that.
Okay. Okay, so it's not like simplified, they're just using not the derivative.
Right, yes, because we don't have to fill out the Wronskian with the rest of the information. We don't have to fill out the matrix. We've got everything with these vectors that we need to put in a matrix. So this is where the Wronskian is kind of the same idea as what we've done before in terms of you got to take a determinant and it has to be not identically equal to 0, but it's kind of different because the way you set up the determinant is a little bit different. Does that help?
Okay. Thank you, yes.
Okay, cool. All right. Other homework questions that people have? Other ones? Anything else? Okay. Then, sorry, Abby, I muted you and you unmuted yourself. We're good. Okay. Then Monday, Friday for homework. Homework is due on Friday. Any other procedural questions before we get going on section 5.4? We're going to do magic today. Anything else? Alrighty then, 5.4. We'll do a new whiteboard here. So Section 5.4, eigenvalue method. People who have had linear algebra, this should sound familiar. Eigenvalue method, eigenvalue method. You liked eigenvalues. We did a lot of these. They weren't so bad, promise. All right, so section 5.4 is the eigenvalue method. Okay, remember where we're at. Here's what we have. We have vector x prime equals p of t times vector x plus vector f of t, right? That's how we have gone to writing a system of differential equations. That's how we're writing this. And remember also what our goal is. Find x1 vector, vector x2, all the way through vector xn, that are two things. First of all, particular solutions. And second of all, linearly independent. That's what the magic that we haven't been able to do up to this point. That is what we are looking to do in this section. Find these vectors x1, x2, xn that are particular solutions and linearly independent. And I should also say, remember we are working with a homogeneous case. So since we're only doing homogeneous, that means my vector f of t is equal to the 0 vector. We said if I had another week left in the semester, we would tackle non-homogeneous, but we don't. So therefore homogeneous only in this case. So if we find these, then we can do a general solution, right? So we can put together a general solution, which is vector x equals c1 vector x1 plus c2 vector x2 plus a bunch of dots plus cn vector xn. And then if we wanted to, we could also do what we did yesterday and use initial conditions if we have them to find a particular solution. So we could do one more step also. That's where we're at. The step that we don't know how to do is this goal right here. Find vector x1, vector x2, all the way through vector xn. That is what we are stuck on. That is the magic that we need to learn how to do. So let's do some magic today. All right, our guess, because this worked really well for the time when we were doing this previously, is if P of T is a constant matrix. So in other words, if it just has scalars, if it doesn't have functions, just has scalars, then our system of equations has constant coefficients. Right? If my matrix P of T just has all scalars, then my system of equations has constant coefficients. Everybody clear on that? Just changing, okay? Baby steps, we're doing baby steps. And I should also say, in this case, we're going to use capital A instead of P of T, just so that we can remind ourselves our matrix is going to have just numbers in it and no functions. So this goes back to the characteristic equation, right? We got really good at this in chapter 2. And in chapter 2, our solutions looked like x equals c1 e to the r1t plus c2 e to the r2t, etc., right? We got all these roots. We put them as exponents. If we had repeated roots, we had to deal with that, and we put a t out in front. We could, that was fine. But in general, I got stuff with e's. Even when I had complex roots, we ended up writing the complex roots as sines and cosines, so we didn't have any complex numbers. But with Euler's formula, we still could have written those complex roots as exponents on e's. We just chose not to. And so therefore, we're gonna say, okay, this worked out pretty well last time. Let's make that our guess again this time. So our guess is that vector x sub I is going to be e to the lambda I t times some other vector v. This vector v is kind of like our unknown constant. I wrote it at the end instead of at the beginning, but up here, all of these coefficients are unknown, right? So I kind of need a vector with unknown coefficients as well. Again, it's at the end instead of at the beginning, but you can kind of pretend that's like one of the constants. And then our guess is that this is going to have an e to the something times t in it. I'm calling it lambda I instead of r sub I, and we'll see why in just a couple of minutes. So if this is our guess, then what we need to do is we need to find lambda sub I, right? When we did this up here, we had to find all the roots. We had to find R1, R2, all those roots. That was good with the characteristic equation. The analog here is that we have to find those same exponents. So we need to find lambda I, okay? So here's how we're gonna do this, and you're gonna get flashbacks to linear algebra for people who have had linear algebra in just a minute. So here's what we're going to do. We know that our vector x sub I, and let me write it, is the v out in front. So v e to the lambda I t. This is a solution to my system of equations. X prime equals ax, technically plus the vector 0. I'll leave the plus 0 off in just a minute. But again, this is a homogeneous equation. And remember that I'm using a instead of p of t because we're assuming that we have constant coefficients, okay? So I need my vector x sub I to be a solution to this system of equations. Are we hanging with me so far? I need vector I to satisfy that solution. All right, so let's look at what happens. If I plug in, I need vector x sub I prime to equal a times vector x sub I. That's what I need. I need that to happen, okay? We can take a derivative. So what we need is the v is constants, so that can totally stay out in front, and then I can take the derivative of this right here. So I need v times lambda I e to the lambda I t to equal a v e to the lambda I t. I'm taking a derivative on the left-hand side, and I'm plugging in my x sub I on the right-hand side. Still good? Still hanging with me? Doing okay? All right, are we good? The e to the lambda I t is never 0, so I can cancel that, divide by that. That's okay, that's fine. So what I need is lambda IV equals AV. That's what I need. So I'm looking for. Okay. Can we arrange a little bit? So let's do some subtracting. I need lambda IV minus AV to equal 0. If I subtract, I'm going to get this on some other side. People who have taken linear algebra, this should be looking more and more familiar. Should be looking really familiar. So I can factor out a v, and I need lambda I minus a times vector v to equal the 0 vector. That's not quite right. We got to fix something in there, but you can copy that down first. I left a space on purpose, and then we'll fix something in here. So I need lambda I minus a times vector v equals 0. Here's the part that I got to fix. This lambda sub I is a scalar, and this matrix A is a matrix. I can't take a scalar minus a matrix, so I need to multiply this by the identity matrix. So you got to put the identity matrix in there. Remember, the identity matrix is the matrix with 1s down the main diagonal and 0s everywhere else. People who have taken linear algebra, tell me this equation looks familiar. It doesn't usually have a subscript in it, but tell me this equation looks familiar? Yes, yes, yes. Okay. If you were in linear algebra, we would prove this next part, but I'm just going to state it as a fact because this is not a linear algebra class. In order for this to happen, this happens if and only if the determinant of lambda I minus A is equal to 0. If you're interested in why that's true, take my linear algebra class in fall. We will talk about it extensively. We'll do a proof. We'll talk about why that happens. So this happens if and only if the determinant of lambda I minus A equals 0. So let's summarize. Here's where we're at, and then we're going to introduce terminology. So my basic equation is going to be x prime, vector x prime, equals A times vector x plus the 0 vector. That's my basic differential equation I'm going to solve. A particular solution is going to be vector x sub I equals vector v times e to the lambda it, where lambda I is the scalar, so that determinant of lambda I minus A is equal to 0, and v is the vector, so that AV equals lambda IV. So we can find a particular solution. This is going to be vector x sub I equals vector v times e to the lambda it. Lambda I is the scalar coming from that determinant equation, and v is the vector coming from that matrix equation. AV equals lambda IV. Terminology for this. Lambda I is called an eigenvalue of the matrix A. So that's what lambda I is called. That's German eigenvalue. And vector V is the associated eigenvector. Okay, so we've got an eigenvalue and an associated eigenvector. And then if, and this is an if there are n linearly independent vectors, maybe I should say particular solutions. If there are n linearly independent particular solutions, x1, x2 vectors through xn, then we can find our general solution. And that's going to be vector x equals c1 vector x1 plus c2 vector x2 plus a bunch of dots plus cn vector xn. So if we have n linearly independent vectors of these, x1, x2, all the way through xn, then we can get a general solution. In 5.4, we're going to look at what happens if we do have n linearly independent particular solutions. In 5.6, we're going to look at what happens when we don't, when bad things happen. So in 5.6, we're going to say what happens if we cannot get n linearly independent particular solutions. Are people caught up with writing? Can I stop sharing my screen and get to see all of you and see how we're doing, etc.? Do not want to clear my drawings. Okay, how are we doing? We totally need to do an example. We need to do 2 examples, but how are we doing so far up to this point? Doing okay? All right, people who have taken linear algebra, basically what I've done is turned this into a problem of find the eigenvectors and find the eigenvalues and find the associated eigenvectors. That's what we're doing here. That's the problem that I've turned this into. Doing okay? All right, we totally need to see an example.